Newton's law of gravitation to define the force of attraction which exists between different objects. And this one is also connected to the general relativity, which is related to the black holes, why the huge masses, they attract everything around them, like black hole. Yes. No, chapter number 6. We are finishing it up. Okay. This is the last topic, including the Kepler law. Okay. We went over the definition of this in our last lecture. I would go over it and extend it further. So the definition for the force between two objects is given by G m1 m2 over r square. R is the distance between the centers of two objects. G is the universal gravitational constant. M1 is first object and second object. And we also know that according to Newton's third law, if one object applies force on the other object is going to apply force on the first one too. So if M1 exerts force on M2, M2 is also going to exert force on M1, which are equal in magnitude and opposite in direction. The magnitude is given by this formula which shows the product of masses and the square of the distance between them. This is an inverse square law. It is applicable to all objects existing on Earth and in the universe. However, since for small size objects, the value is going to be incredibly small due to the smallness of G. Okay, because the distances that we usually deal with, they are not very long distances on Earth. They are not very huge masses on Earth. This is not like we are talking about the mass of the sun or mass of any planet or something really huge. When we talk about those kind of attraction forces, for those masses, this becomes considerable big, and that is responsible for moving the planet in the path that it should be. From here, we also came up with the formula for G m E over R E square, and this is another way to check the value of acceleration due to gravity. So everything falls towards the Earth, but remember, this is the mass of the Earth. This is related to the acceleration due to gravity due to Earth's attractive forces, that the force that Earth is applying on any object to move it, and it gets accelerated at a constant rate. We also looked at the G value. It should decrease with RE square as if the H increases, decreases as the distance above the surface of Earth increases. This RE, when we derived this formula, we took this RE because we were talking about an object sitting right on the surface of Earth. So the distance was naturally the radius of the Earth. But if this object is raised to some distance, if this object is not here, instead of that it is here, then RE plus H would be the total distance. When H increases, the G value will decrease. And by plugging in this value, by knowing this value of G, mass of the Earth, radius of the Earth, or plugging these value in can generate the value for G at that position. Now, can we use it finding the Earth's gravitational pull at different distances? Yes, we can. Let's try to find it on the surface of Moon. find G value at the surface of moon. What information do you need in order to solve for it? So here is the Earth and the moon, Earth radius plus this. What kind of information do we need? We need the total distance from the Earth, correct? Because it's going in an orbit. We can assume this orbit is a circular orbit, but it is most likely elliptical orbit. But this is considering this would be the radius, which varies by some value at different places. But we do need to know how far the moon is from the Earth, correct? On average, this distance does vary. It's not a perfect circular path. So once we know this distance and we know the value for Gm divided by R square, we have G 6.67 times 10 to the negative 11 divided by a mass of 6.6 kilograms. R square, okay, R square value, the distance of moon from the Earth is 3.84 times 10 to the 8 square meter. Now this is the value that you can find anywhere on the internet, just finding the distance of the moon from the Earth. Plug that in, that generates a value of 2.70 times 10 to the negative 3 meter per second square. See how small this is, because the distance has greatly increased. So G was, what was G at the surface of Earth? What was G here? 9.8. And what's the G here? After traveling this long distance, this has reduced to this small value, right? So G is not a constant. It varies with the altitude. As you go way above the Earth, there is not enough gravitational pull due to Earth. That decreases. Now, if we want to know, okay, moon goes in a curved path? Yes. Can we figure out what's the centripetal force on it? What is the centripetal force on it? Which force is providing the centripetal force? Centripetal force does not exist. It's not a special kind of force. We know that. It comes from another force. What's that another force? Gravitation, right? Mass of the Earth, mass of the moon, distance between them. Can you try to figure out what is the centripetal force acting on it? Radius time what square? The formula for acceleration. We do need this. Even if we are doing the force, we do need this. Correct? Is that right? If we are doing the force, all we have to do is adding the mass of the moon on both sides. That's what the force is. But we do need, what is this V? Is the speed of the earth? Speed of the earth? The moon. Because the centripetal force is applied on the moon. We are working for the moon. We are not talking about the acceleration produced in the earth. We are considering this is a huge mass sitting at the center and moon is going about it. So what's the centripetal force acting on it? That distance from the earth. Correct? My question was, what is this speed? Is it angular speed, linear speed? It is in a circle, yeah. Tangential speed is the linear speed. This is the tangential or a linear speed. V is representing the linear speed or tangential speed. Okay, it's not omega. It can be written in terms of omega, but it's not. Now we do need this tangential speed or linear speed or orbital speed. That what is the speed of when you look at the number of Earth's orbital speed, this is what you are looking at. How fast it's going in its orbit. So if we want to know, is there a way to find out the speed? If we know the time and if we know the distance, can we find the speed? Yes, correct. Do we know the time moon takes to go about the earth? Roughly, it's actually the actual number is 27.3 days. So the time period is 27.3 days. If we want to work with accurate numbers. Is it the regular time or is it some different time? It's a time period. How time period is different from regular time? What's the difference between this and this? Big T? Yes. Big T is a time for one rotation. Small t is the variable. It could be any time, at any instant. T is a specific number. It tells you to take one complete rotation, how much time it has taken. So we could use, can you convert this days to seconds? The number? You got the number? If you calculate in 24 hours multiplied by 60 multiplied by 60, there are 86,400 seconds in a day. So if you multiply that number by 27.3, that's going to give you the time in seconds. So you need to find omega. Delta theta over delta t, where delta theta is 2 pi, one complete rotation. T is time period to do one rotation. 2 pi. Just plug in all the numbers and you should get the value of omega equal to 2.66 times 10 to the negative 6 radians per second. Good? What did... 2.66 10 to the negative 6. If someone should be doing calculation with me. Yes. Delta theta, because that's the definition of angular velocity. How many radian? Because time period means it's one rotation. 2 pi is, yes, it's the time. T is the time to complete one rotation. What would be the displacement in that one rotation? 2 pi. Correct? Right? And it's whatever is in pi, is it in radians? 360 degrees. If somebody has worked with the other formula that we learned the other day, finding V using 2 pi R over T, that would have generated the same answer too. Okay, that is you just find the orbital speed by plugging in 2 pi, and R is the distance, and T is the time period, that same that you used in this here, 27.3 days multiplied by this number. You could have plugged that in, found the V directly. Okay, or we can do it this way. AC is equal to V square over R. V is equal to R omega. Do we know that already? V is equal to R omega. That is a connection between the linear speed and the angular speed. One R gets cancelled, R omega square. You just use the value of R, use the value of omega, plug in the values, you will have the centripetal acceleration. Do we know R? .84, yeah, 3.84. That is the distance of the moon from the Earth, meters. Omega we just found, just plug in the numbers, find the acceleration. Tell me, what acceleration do you get? You have the value? 10.2? .7 times 3. Does it match with any of the value you found in this problem? The gravity. So how much the gravity was reduced at the surface of moon? It was reduced to 2.7 times 10 to the negative 3. And this is what you are getting for centripetal acceleration 2. What does it mean? Exactly. The acceleration is provided by the gravity, right? The force of gravity from moon to earth, the acceleration is provided by that force. This is equal to or proportional to g. G value at the surface of moon from earth. Okay, we are not using the mass of the moon, we are not using anything or radius of the moon. We are using the distance from the earth. We are using everything related to the moon, but we want to know what would be the gravity at that distance. And that turns out to be providing the necessary centripetal acceleration to that moon to be on that circular path. If there is no centripetal force on it, it will never go on a circular path. Which way will it go? It will go home. Which way? It should follow the tangent line. At every point it should follow this tangent line, wherever it is. Good? It's very interesting. I found this problem very interesting. Because we always say that the centripetal acceleration of force is given by the force of gravity or the force of gravitation, but this is a proof for this motion. This necessary centripetal force is coming from the gravitational forces.
So is that always true if the centripetal force is given by the force of gravity?
Yes, in these cases, yes, but not for something like you have attached stone with a string, moving it, that's tension, that's not force of gravitation. But you see, there is no link between moon and the earth, but moon is still going in a circular path. So there must be a very strong force between these two, which is invisible to us, but it is still putting it in a circle. Nobody could go in a circular path if there is no force on it. And that force at that long distance must be very strong. And Newton worked on it and he called it the law of gravitation.
So two are attached objects and one of them
Exactly. Remember in the beginning we said some forces are the contact forces, some forces are the non-contact forces. You can't see them, but they are there. It's one of the non-contact forces. The gravity, it's a beautiful example. Electric forces, we don't see them, but we know they are there, right? Tension force, normal force, they are all the example of the contact forces. These are all the invisible fields around us, invisible lines. Perfect Halloween theme. Are you all getting ready for Halloween? Okay. Is it do we have a lecture that day? We do? That's interesting. You are Sullivan.
Yes.
Okay, so Sullivan said if there is no external force on the object going in a circular path, it would go in a straight line. Right? We all agree with that. What speed does it have around it? It does have a tangential speed. It's also called linear speed. You can also call it orbital speed, but as long as you're talking about not related to the rotation, this V can have different names. Now, sometimes when we are on, let's say, on the merry-go-round, and there is something sitting on the floor. So, I mean, I could use the same example for the merry-go-round, the circular path, and then there is something sitting on the floor which is like maybe a leaf or something on the floor. Obviously, this leaf is not attached with the merry-go-round like the other things on it. But what should be? We know that when it is rotating, for example, it's rotating counterclockwise, would there be any force on that leaf? Yes, no, maybe. It's sitting on that platform, it's moving with it, it should have some force on it, correct? That is the same as add that if it is sitting at a distance of maybe 15 centimeter, it will have, you can calculate its speed, you can calculate everything for that leaf. However, sometimes when the merry-go-round suddenly speeds up, accelerates, okay, when it accelerates, sometimes it is noticed that it would fly away. And if you observe it from the platform, it feels like it went the opposite way. Okay, this is, sometimes it is called the centrifugal forces. But these centrifugal forces, these are not real forces, okay, are not the real forces, because they are observed from non-inertial frame. Now, what do I mean by non-inertial frame? Accelerating frame, rotating frame. It doesn't mean that it's at rest or at constant speed. It's an accelerating frame. So due to that change from being observed from the inertial frame, non-inertial frame, which is the merry-go-round platform in this case, that force feels like it went away. We often feel that when we are turning the car to the right and the driver is pushed to the left, that also feels like there is a force on the other side. But that force is also not a real force. That only due to what? Inertia, right? You turn right and then there is a force felt on the left-hand side. There is no force acting. If you observe it from the earth frame, if somebody is observing it from the outside, there is no force on it. What is felt is there is only this force on it, centripetal force on it, and if it moves, it's always going to go along the tangent line. Then why it goes away? Why the object did slide? Because it was not connected to anything. There was nothing to keep it. There was not enough friction between this and the floor of the platform. If you put something heavy there, it might stick there even if it goes very fast, but something very light, not having the enough friction, not having the enough centripetal force, it moved away. Due to lack of centripetal force, not because the absence of the centrifugal force. It's not that there was no centripetal, there was some centrifugal force acting on it that put it away. No, it's the lack of centripetal force. There was not enough friction in this case which could put it in that path. So centrifugal force is not real, but it does have a lot of application. The centrifuge machine, which goes at very high angular speed, when it moves, what happens to the sediments in it? They cannot move, so they separate out. So faster it goes, the faster they are separated from the rest of the material based on their masses, because they are the loose particles, so they cannot go in the same speed with rest of the liquid, and they chemists often use this method in order to separate all the particles in a mixture where they have different masses. The centrifuges move so fast and they cannot go at that speed, so they get sedimented at different radii. There is another force which is often observed, mostly for observing the weather, is the Coriolis force. Coriolis force is also a force observed from the non-inertial or accelerating frame of reference. We called, if you remember first of our lectures, I said we will be making all of our measurements from the Earth because Earth is moving very slowly and we consider that it is at rest. Even though we know that it is not at rest, it's constantly accelerating. But that acceleration is small. So Earth is also not a perfect inertial frame of reference. So if we bring that into account, or reality of the Earth into account, then anything that is passing or the Earth's surface that would be subject to those fictitious forces. Now, if we observe the Earth from the top, from the northern hemisphere, it feels like it's going counterclockwise. So the objects will be tilted to the left. Okay, observe from the top, it's going to the, oh no, it's counterclockwise. Oh, it will experience force to the rightward force, sorry. From the southern hemisphere, it is also, so if we observe it, it's going to go clockwise. So they will feel a leftward force. These Coriolis forces are important for the wind or hurricanes, how they turn around, because you have seen them going in a circular path. So when they turn to the left, they start going in that rotation. But that force does come from because of the rotation of the Earth, and that is affecting those light bodies, which is like air masses, fast winds. They will be affected by the Coriolis force. But Coriolis force is a force which is from the rotating frame of reference of Earth. Last topic, Kepler's laws. Kepler gave 3 laws for planetary motion. These could be applied to any system. You can talk about planet and the moon. You can talk about Earth and its moon. Any 2 objects which are compelled to go in an orbital path. One of them is considered as a huge mass and it's not moving. The other one is the one which is moving in a circular path. So there are some conditions for the Kepler laws to be applied. One of the masses is large mass and stationary. And obviously that mass is also not stationary, that is also spinning. That means it is the inertial frame of reference, it is at rest. Okay, and other mass is the mass in the orbit, which is rotating. So it is something like this. You have a huge mass, you consider it as a stationary, you will be making observation from the stationary, and then there is another mass going in a orbital path, which we could call small m. Okay, so this is one of the conditions. If this is not satisfied, obviously the numbers could fluctuate from the values that we expect. Number 2 is system is isolated from other masses, so they do not apply any gravitational forces on each other. Like if you're talking about the Sun and the Saturn, these are the only two in your system. You will consider the system isolated from the other planets. Once these two conditions are satisfied, there are 3 laws which define the orbital motion. Your book has only given the statement of each law, and the 3rd law is explained a little bit more. Okay, so this is what we will do too. We will have their statements and one derivation. The orbit of each planet around the Sun is elliptic with Sun on one focus. Okay, it is something like that. The path is, so these are the realistic description of the path. It's not circular for most of the planets. It is like an ellipse, and ellipse has 2 focuses. So Sun is located on one of them. So at some positions it's going to be close to the Sun, at some position it's going to be really away from the Sun. Okay, second law, the planet sweeps equal area in equal time intervals. If you pick 2 different locations, it is going to sweep. Let me use the same picture for explaining this as well, but if you want you can make a new picture. So if the planet is at this location and it has swept some area A1, and but over equal time interval, and this is A2, the law says it will cover equal amount of area when it is closer or away. So it's going to be very thin strip when it is away. It's going to be very wide strip when it is closer. But at the end, the area covered should be the same over the equal time intervals. third law is more mathematical. First two laws, they do not really have any mathematical form linked to them. They're just the statements. Third law, it is the statement. The ratio of the squares of the time periods of two planets. Okay, remember, these are time periods, time to do one complete rotation. They are proportional or equal to the cube ratios of their distances from the sun. Let me write down for each one of them. These are the time periods for planet 1 and 2. These are the radius or let's say distance of planet 1 and 2 from the sun. There is a table in your book where they have given you, based on the experimental evidences, they have given you the ratio for the time period of different planets which follow this relationship. This one does not have any background associated to it. However, this can be derived using the formulas that we already know for the gravitation or the centripetal forces. Squared. Sorry, say it again. Yes, sorry. Yes. Thanks for the correction. Yes, they are squared. T2 squared. Okay, and these are average distances because the distances are also elliptic. So average distances of planet 1 and planet 2 from the Earth. This can be derived using centripetal formula mv square over r, applying it to each planet. First, we will get the value just for general description. So this centripetal force comes from the gravitation. R gets cancelled, small m gets, so basically mass of the planet gets cancelled, but the mass of the sun stays. Gm over R. Now you can notice we do need the time periods involved. And we know that for average distances, we can use V as total distance traveled in one revolution over the time period, right? Distance over time. We can plug that in here. 2 pi R over T square, Gm over R square. And what are we left with? Gm over 4 pi R square, R square.
Did we get G over R squared equal to 2 pi R over T? Because I thought you had just
Oh.
over R.
Yes, R cube over T square. Yes, that would have messed up the whole formula. R is just 1 from one end. So this one is simplification. You can work on it yourself, but R square will be multiplied by this, making R cube. This is T because of this square, that becomes T square. And this is a constant value. So comparing two orbits, planet 1 and planet 2, you can write it as R1 cube over T1 square, Gm 4 square equal to R2 cube over T2 square. So comparing their ratios, since they both are equal to the same constant, R1 cube over T1 square is equal to R1 cube over T2 square. We can further adjust it. We can put the T1s, T2s together and R's together. This is R2. All right. We can just leave it in this form, or we can just take this one here, bring this one down here. It would be the same thing. The ratio of the square of the time periods for both planets is equal to the cube of the average distances from the sun. All right. This ends chapter number 6. We will move on to chapter number 7, work and energy, in next lecture.